Hey guys, welcome to lecture number 22. In this second lecture from the fifth chapter, we will be talking about the definite integral. But for us to define the definite integral, we need to talk about the area as the limit of a sum, and also we would like to talk about Riemann sums as well. So let's get started. I would like to start with talking about the area as the limit of a sum. So let's get started. And so let's start with this. So the area, so first we'll be talking about the area as the limit of a sum. Okay. Well, let me. So first, suppose that suppose we need to compute the area of the following shaded region. The area of the shaded region, and let me draw some graphs. And let me just draw it here. So, and suppose we have the graph of a function which goes like this, right? And suppose we have something like this. So the area of the shaded region in this case, so it's this guy here. This is the shaded region. And we would like to compute the area of this, right, of this shaded region. And how are we going to do this? What we will do is the following. We're going to break up into rectangles. So the procedure is the following. I'm just going to say it here. We're going to break up into rectangles. And the picture would look like this. So keep this in mind. And now I'm going to draw another one. Which will be something like this. So let me just draw the picture again. In fact, okay, so this is the graph of f. And as you have seen, it was something like this. And now we're going to break this into rectangles. Maybe I should draw this a bit, okay, like this. All right, so what we're going to do is the following. So we're going to break this into rectangles. As you can see here, I have to go like this, right? Here I'll do the same thing. The same I'll do here. And same here. And then at some point, right, I'll have something like this. Okay, so we break this into rectangles, and now let me show you. So this part here, right, as you can see, it's the same goes here. Again, same here. And the same here, right? As you can see. Okay, that's great. So in this case, if you look, we have how many rectangles? Let's suppose we have 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay, so we have 8 rectangles, and we can say in this case that the area, in fact, we can say that the area was approximated right, by 8 rectangles. This is important. You see? However, the area given by rectangles, given by these rectangles, given by these rectangles, okay, is, let's say, a little bit higher than what we expected. Than what we expected. Okay. All right. So that's the picture. And now I'm gonna just do it like this. As you can see, I'm gonna deal with the area of these rectangles. And the same will go here as well. Right, and we keep going. We're going to do the same thing for all of them because we're interested in the area of these rectangles. Okay. And all right, so these are the rectangles, as you can see. All right, and now what we're going to do is the following. So we're going to draw another one, another picture. And I have to be, so what we're going to do is the following. We're going to increase the number of rectangles and the area, right, the area estimate is improved by taking more rectangles. And let me draw another picture. And again, suppose we have the graph like this. And now I'm going to do the same thing. I'm going to take more rectangles now. So let me just take them like this. Like this, this. And we keep going. And we keep going until we have something like this. And so on, right? And then we can say the same thing. So the area of, okay, I'm gonna draw, right? So we can say that if we increase the number of rectangles, the area estimate is improved. So we can improve the area by taking more rectangles. And you will see that we will do this as a general approach, where we'll take more and more and more rectangles, and we'll try to approximate this area. But anyway, we'll get there. And you will see that this is what we will call a Riemann sum. And now let me just say a few words about the general approach. So the general approach scheme is the following. All right, so here is a story. Suppose that we compute the area under the graph of the curve, the area under the graph of the curve wait, let me, no, it doesn't make sense. Suppose we compute the area under the curve curve y equals f of x on the interval, let's say, AB. Okay. And where it's important to say that where f is non-negative, when f is a non-negative continuous function. And now we're going to do the following. So step one, we partition the interval AB into n equal subintervals. So that's the first step. And the length of each subinterval will be with the length. And we're going to denote this in the following way. We're going to write this as delta x, which will be b minus a over n. So this will be the length of each of the subinterval. We can say it's the width of a rectangle. Okay, so that's the first step, right? All right. And now let me just draw a picture so that you can see it. So we're going to have the following picture. So that you can see exactly how the length will behave. So let me just draw a larger picture. Okay. All right, so let me just draw something like this. Suppose I have a graph and goes like this. All right. And now, and I have this function, let's say here is the interval AB. Okay. And now, let's suppose I have here, let's say I have here a value a plus delta x, right? And let's just suppose I have here another value, okay, a plus 2 times delta x. Okay, I have the double of this. Okay. And here, well, here I'll have, let's say, here the point will be f of a plus delta x. And here, let's just say I have f of a plus 2 delta x, right? Okay. All right, so we have this. And now, well, we just put this point on the, in fact, I should have, the graph is not the, okay, let me draw it like this so that I can catch these 2 points here. Okay. We'll go something like this. All right. Let me just say something like this. Okay, so this is the graph of f. All right, so here is the point of coordinates a plus delta 2x and f of delta plus 2x, and this is the, okay, let me just do it here a bit. Let me just draw it again nicely. Okay, that's more nicely, okay. All right, so you see the difference between from a to, from a plus delta x from here to here is nothing else than just delta x. So that's the difference. And the same goes from here to here. It's again a delta x. Well, if you want to measure the difference, the distance from a to a plus delta x, it will be obviously will be 2 delta x. And now you're gonna express this. You'll try to write this as areas of rectangles. If you look here, if you're trying to write this as express this as rectangles, right? As you can see, we have some rectangles formed here. Well, if you want to look at the first rectangle, right? So the first rectangle will be this one. Let's call this R1. As you can see it here inside. So this guy will be R2 if you want. And you can keep going, R3 and so on. But anyway, let's just stick to R1 and R2. So, and you can keep going, but anyway, let's just say the area of the first rectangle so the area of the first rectangle will be nothing else than just what? If you look, so that will be delta x. So it will be from here will be f, from here is 0. So it will be delta x times f of a plus delta x. All right, great. Now let's see the area of the second rectangle. The area of the second rectangle is nothing else than, if you look, it's again delta x, but it will be, so f of, so it will be delta x times f of a plus 2 times delta x. And we can keep going inductively. We can say that the area of the nth rectangle will be nothing else than just delta x times f of a plus n delta x. And now, if we want to sum up to see the area, the entire area covered by the interval AB, right? We're going to, let's just call this a sum. So the area covered by the curve on interval AB let's just call this S sub n, right? And we have that S sub n is nothing else than just, we add this area of R1, R2, R3, and so on. And so on. So this would be f of a plus delta x times delta x plus f of a plus 2 delta x times delta x, and we keep going, plus so on. And the last one will be f of a plus n delta x times delta x. And this is how we can express the sum of all areas of those rectangles. Okay. So we can say that as we increase that, okay, let me put it like this. So we can say that we obtain a better estimate as we increase the number of rectangles. For example, if we increase, well, let's say the number is n, but if we like to see n for n big enough, what happens? So as n approaches infinity, right, for n large enough, it follows that, in fact, let me write this in color because it's important. So as n approaches infinity, delta x will approach 0. This is important for you to know, right? So you just look at the picture, you have only two rectangles here, but imagine that we break this into n rectangles, right? Well, for example, we keep going here. Okay, let me just show you like this, and then we go like this and so on, and we keep going. All right. Well, I think this formula is very important because we just add the area of the rectangles. And as you can see, there we have a common factor. But anyway, not yet. Let me just say, no, well, as you can expect now, the area, we will talk, okay, let's talk about the area as the limit of a sum. Okay, so we'll have the following. So the area will be nothing else than the limit as delta x approaches 0, right? Because we have seen previously, look here, as n approaches infinity, delta x will be small enough, so we'll approach 0, right? And this will be nothing else than just the limit as delta x approaches 0 of Sn, basically. And let me just write this. Okay, let me write it in this way, of Sn, which will be nothing else than the limit as delta x approaches 0 of f of a plus delta x times delta x plus f of a plus 2 delta x times delta x plus f of a plus n delta x times delta x. Okay, and we keep going. So this would be, okay, let me write like this. So the area will be nothing else than the limit as delta x approaches 0 of, well, I can write this in this way, the sum from k equals 1 to n, and I can factor a delta x. As you can see in the previous equality, we have a common factor, delta x. So this would be a delta x times an f of a plus k times delta x, where delta x, we know who delta x is. Look back at the step 1. You see, delta x is nothing else than just b minus a over n, where delta x is b minus a everything over n. All right, so this is the formula that you deduced. Well, you don't need to know it by heart as long as you know how to deduce it, but if you want to know it by heart, it's fine. Either way. But I want you to look at it because this is the very important formula. All right. And now let me just, because I use this the summation notation, and I feel like we need to talk a bit about this. So this guy here, this is important because I'm not sure if you're used to it. So this guy here is the summation notation. Right? And now let's just talk about this. Let's just say a few words. So the summation notation. Okay. Now, well, it's pretty clear. When we have something, when we add A1, these numbers, A1 plus A2 plus AN, instead of writing all the time A1 plus A2 plus AN, I can write this in a very concentrated form. As this, I'm going to use this symbol, sigma. It comes from Greek letter sigma, from k equals 1 to n of ak. So this n here is the upper limit of summation. And this k equals 1 here is the lower limit of summation. Right? And this guy here, this is the general term of the summation. So this is a general term of the summation, As you can see, the index is the k index. Let me be even more specific, right? So that's the notation, the summation notation. And now let me tell you some rules about, so we have the following theorem, which is important. And this theorem will address exactly the rules for summation. So the theorem states the following: for any numbers, let's say C and D, and positive integers m and n, we have that we have the following. And now let me do it like this. Let me draw the following table. So the first one here is the constant term rule. Right? Which says the following. So if you sum, let's say we have a constant C, and you sum up from k equals 1 to n, this constant C, this will be nothing other than just C plus C plus C plus C, and you have here n terms, and this will be nothing other than just n times C. Okay, now the second one is the sum rule, which says the following. All right, let's get back. So the sum rule, right, is the following. So we can write this as the sum. So we can use this sigma, the sum from k equals 1 to n of ak plus bk. So we have two terms here, right? And we can say that this is the sum of ak from k equals 1 to n plus the sum of bk from k equals 1 to n. Okay, this is the sum rule. Now we have the scalar multiple rule. Which says the following. So it says that the sum of C times AK, K equals 1 to N, is nothing else than just C times the sum of AK from K equals 1 to N. So we can write it like this. Okay. So you can take the scalar out. So that's what you need to know. Let's see, what else is there? Linearity rule. So let's just say we have a combination of the second and the third rule. So we'll call this linearity rule, which says the following. So if we have the sum of, let's say from K equals 1 to N of, and now we can write in the following, C times AK plus D times BK, this would be nothing else than just C times the sum of AK plus D times the sum of BK. All right. Okay. And now let's call this the subtotal rule. Anyway, I wouldn't have called it like this, but the fifth one is subtotal rule. And this says the following: if, let's say, m is less or equal than n, but greater than 1, then we can write that the sum of AK with K going from 1 to n. This would be, we can break the sum into two parts, let's say from K equals 1 to m of AK, plus the sum from K equals going from m plus 1 to n of AK. So we can break the sum into two sums. And the last one, it's what we call the dominance rule. So 6, this is dominance rule. And this is important as well. So if we have, let's say, AK, which is less or equal than BK, so we say that BK dominates AK for K equals 1, 2, and so on, n, then definitely we have that the sum of AK is less or equal than the sum of BK. Right? All right, so these are the rules that you need to know. And now let me give you some summation formulas. So I want you to look at them again. So these are the rules. Well, they're pretty straightforward. It's I'm sure you can. And now let me talk about summation formulas. These are very important. So summation formulas. All right, and I'm going to write this with a different color. The first one, and very important, is the following. The sum, well, as you can imagine, from K equals 1 to n of 1. So in other words, we say that add 1 by itself n times. So this would be 1 plus 1 plus 1 plus 1 n times. So here I have n terms of 1 added together. So this would be nothing else than just n. The second one, the sum from K equals 1 to n of K, this will be 1 plus 2 plus n, right? And it will have this from n times n plus 1, everything over 2. The third one is the following. The sum, let's say if we add this first n squared numbers, so the sum from K equals 1 to n of K squared, this would be 1 squared plus 2 squared plus all the way plus n squared. And this would be n times n plus 1 plus 2n plus 1 over 6. Right? Okay. And the last one is the following, is the sum of the first of the cubes, which is y1 cubed plus 2 cubed, and we keep going all the way to n cubed, and this would be n squared times n plus 1 squared, everything over 4. All right, so these are the summation formulas that you need to know, and they're very important as you will about to see in applications. And now let's see an application. So let me write this. So example 1. All right, now I'm going to consider the following. I'm going to consider the simplest parabola. So let y be x squared, right? And we would like to compute the area under the curve, the curve on interval 0, 1, closed interval 0, 1. As you can see, the curve is clearly y equals x squared. All right, so how are we going to do? Remember that the area had that formula. Let me go back to it. You see, look at it. You see the area, it has this formula here. As you can see, we have the delta x times f of a plus k delta x, and we know that delta x is b minus a over n, and we sum up all these, and then we take the limit as delta x approaches 0. All right, so that's what we need to do, right? Okay. Okay, great. So let's do it. All right, so we know that. The area, which is the lim as delta x approaches 0, of the sum from k equals 1 to n of f of a plus k times delta x. Anyway, and we know how to identify in our case. So in our case, a is 0, right? Because the interval is not a, b is 0, 1, and b is 1. All right, so the area will become the following. It will be the lim as delta x approaches 0 of the sum from k equals 1 to n of f of k times delta x. This is important. And now we have to see who so we know that f of x is x squared. Moreover, since f of x is x squared, right? Because y equals f of x is the curve in general. It follows that that f of k times delta x will be nothing else than just k delta x everything squared, which is nothing else than k squared delta x squared. All right, and now we can plug it in, and thus the area will become the following. So a will be equal to the limit as delta x approaches 0 of this sum from k equals 1 to n of k squared times delta x squared times delta x, which will be nothing else than the limit as delta x approaches 0 of the sum from k equals 1 to n of k squared times delta x cubed. All right, so we got to all the way to this point, but now we haven't used any information about delta x, so we don't, well, we know who delta x is, so, but we know that, remember at the beginning I told you in step 1, we know that delta x is b minus a everything over n, which is 1 minus 0 over n, which is 1 over n in our case. And now this limit will transform into, so we can write the area. So instead of writing delta x goes to 0, we can write as 1 over n approaches 0 or n approaches infinity. So this will be the limit as n approaches infinity, right? We said that as delta x approaches 0, as n approaches infinity, delta x approaches 0 and the other way around. So they're equivalent. So this will be the area will be the limit as n approaches infinity, right? Okay, of, and now let's write the sum. So it will be the sum from k equals 1 to n of k squared times, you see, delta x cubed. So we have 1 over n, everything cubed. And this 1 over n will be a constant, so let's take it out. So this would be nothing else than just the limit as n approaches infinity of 1 over n cubed times the sum from k equals 1 to n of k squared. And now it's clear what to do. We just have to go back to the sum. As you can see here, we have this sum, the sum of the squares. And if you go back, you see number 3 here in the summation formulas, we have it there. So we can plug it in. So this would give us that this is equal to the limit as n approaches infinity of 1 over n cubed times the sum of k squared will be n times n plus 1 times 2n plus 1, everything over 6. So this would be the limit as n approaches infinity of n times n plus 1 times 2n plus 1, everything over 6n cubed. Well, then we would like to compute the limit of this, right? And I think I showed you the limits when we dealt with limits of functions, so we can factor n to the highest power on the top and the bottom. So this would be nothing else than just the limit as n approaches infinity. So let's do this. So I have here n cubed, and this would be times n cubed times what? Times n cubed over 6n cubed, and this would be times 1 plus 1 over n, right, times 2 plus 1 over n, right? So I'll have here, anyway, so this would be nothing else, these two will go away, will be nothing else, as you take the limit as n approaches infinity, this would be 2, okay, I'm sorry, it will be 2 over 6, which is 1/3. So the area is 1/3. So now let's go back to the problem. So the area under the curve on the interval 0, 1 of this curve here is nothing else than just 1/3. Anyway, and you can do the same thing for example, if you take y equals x cubed. So you can apply the same procedure. The only difference is that you will have to deal with the sum of cubes and so on. And you can just play around with any function you want. Well, if you have like a much more complicated function than a polynomial function, you know, you have to deal with some sign and so on. But anyway, in our case, we just deal with polynomial functions. All right, now let me veer towards one of the most important material that we will cover in this chapter, and that is, now I would like to veer towards the Riemann sums and the definite integral. So let's talk about this. So the Riemann sums and definite integrals. Riemann sums, well, it's something unexpected and discovered quite late, I would say, by Bernhard Riemann. He's a very famous German mathematician. Well, basically, he didn't write too many papers, but with his papers, he changed the face of mathematics forever, and that's I know that this is a pretty bold statement, but it's kind of true. Well, it is true. So let's talk about this. You will see that this will involve things that we have discussed so far. So let's start with the Riemann sum. Let's see what this is all about. All right, so the Riemann sum, and suppose that a bounded function, and this is important, bounded f, so a bounded function f is given along with a closed interval AB, a closed interval AB. Again, this is important. On which f is defined. Okay. All right. Then we have the following, and I'm going to write it like this. Step 1, because there are a bunch of things here that we need to define here. So the step 1, what we're going to do is the following. We're going to partition the intervals, the interval AB, into n subintervals. So partition the interval AB into n subintervals. Okay, this is important. And okay, by choosing the points, let's just say we're going to choose this point x1, x0, x1, x2, all the way to xn, right? And these points are arranged in such way that we're going to have the following inequality. So let me write it like this. So A will be x0, and this will be less than x1, less than x2, and we keep going. And this will be less than, let's say, an xk minus 1, less than xk. And we keep going all the way to xn minus 1, which is less than xn, which is b. So this will be what we call the partition, right? Okay. And call this and call this partition P. So this is a partition of the interval AB, right? So basically you divide or you partition, whatever you want to call it, the interval AB into n subintervals by choosing the points x1, x0, x1, and xn. But by the way, I want to point out a remark here, and this is very, very, very important. Let me write it with the red. Very important remark that the n subintervals do not need to be equal, to be of equal length. Of equal length. This is important. So I don't need to partition in 0, 1 over n, then 1 over n, 2 over n. No, I can partition 0, 1 over n, then 1 over n, and 5 over, or 300 over n, whatever. It doesn't really matter that much. All right. Okay. Now, let's continue. So we have this partition. This is important. And now for k equal 1, 2, and so on, and n, the width of the kth subinterval is, we're going to call this delta xk, and this will be nothing else than just the difference of any two consecutive. So just look at here, of these two terms, right? X sub k minus 1 and x sub k, and we're just going to take the difference, their difference. So this would be xk, oops, sorry about that, xk minus xk, x sub k minus 1. All right, great. Now the largest width is called the norm of partition P. And we're gonna, this would be the following. So we're gonna, okay, let me write it like this. So this will be the norm. We're gonna write it like this. So this is the norm of P, and this will be nothing else than just the maximum over all k from 1, 2, and n of all these numbers, delta x k. So this is how we define the norm of a partition. This is important, right? All right, and now let me just draw a picture because I want to show you how geometrically how this works. So keep in mind, this is step one. So we define a partition, and we would like to consider the norm of the partition. So the norm of the partition is nothing else than just the maximum of each width of the subinterval, of the rectangle, basically. So now let me draw a picture. So everything, I'll draw a larger picture because I'll have many things here. So let's just say, okay, so I'm starting from the interval here and all the way to here. So this would be A equals x naught, and this will be B equals xn. And let's just say that the graph goes like this, right? So, oops, this would be something like this, right? All right, now I'm going to consider now another point here. Let's just say x1, right? And then we go with x2, and then x3, then x4 if you want. And we keep going all the way to xk minus 1, and then xk. So like I said, they don't need to be equally distanced. And then we keep going all the way to xn minus 1, and the last one will be xn, right? All right, so we have here. And now what we're going to do is the following. So between these points, let me write it with red, I'm gonna have something like this. So I'll have a point here, let's say x1 star, another point, so between x naught and x1, I'll have an x1 star. Then I'll have between x1 and x2, I'll have an x2 star, right? And again, again, we'll have some points here on the graph. And then here I have an x3 star. And I keep going, I'm keep going. And then I'll have between here I have an xk star, right? All right, and the last one I'll have here I have an xn star. and so on. So these are the numbers. And then, of course, I'll have this is f of x1 star. Then here I'll have and somewhere here I'll have f of xn star. This would be f x1 star. This will be f of xn star, as you can see. Then I'll have f of x2 star if you want, f of x3 star, and this here I'll have f of xk star. Okay, I hope the picture makes sense. But as you can see, it doesn't really matter the way we want. You see, you don't have to have them in order. So you can have x1, x0 less than x1, less than xk, and so on. But with f of x1 star, it doesn't really matter. All right, and now the only thing I like to do, if you look at the difference between these two here, right, between xk minus 1 and xk, if you look closely, this will be nothing else than just delta xk, which is the difference between them. All right, so with this picture in mind, and I hope it makes sense, let's go further. So step 2, right, so this was step 1 here. Right, we're just going to consider the partition and then so step 2 is the following. So now we're going to choose, so as you can see here, I put these numbers x1 star, x2 star, x3 star. This is what we will call the intermediary points between those subintervals. So now what we're going to do is we're going to choose a number. I want you to look at the picture because it's so we're going to choose a number arbitrarily. So arbitrarily from each subinterval. Well, as you can see in the interval, the x0, x1, we're going to choose x1 star. In the subinterval x1, x2, we're going to choose x2 star, and so on, right? All right, and now for k equals 1, 2, and n, right? The number, let's xk star, chosen from the kth subinterval, xk minus 1, xk, right, is called so this will be is called the kth subinterval representative of the partition P. Okay. And now in step 3, well, as you can see, it's the picture, it makes complete sense, right? And now in step 3, we form the sum, we form the Riemann sum. That's what we, and the Riemann sum will look like this. Rn, this is the Riemann sum, Rn from Riemann, is f of x1 star times delta x1, you can see we take the difference on each subinterval, plus f of x2 star times delta x2, and we keep going, plus f of xn star times delta xn, and or if you want to write this with the sigma notation, this would be the sum from n equals 1 to n of f of x k star times delta xk, right? All right, so this is the Riemann sum. So we form this sum. Well, you will see that something will happen to this sum as n approaches infinity. You will see that this will converge to something. But anyway, I'm not going to divulge anything yet. I'll keep you in suspense. So before that, let me take an example. Let me do this very innocent example. Well, I'm going to say the following, but I want you to look at the formula, so to keep this in mind. The interval, let's say, let's just take, for example, -2, 1, right, is partitioned into 6 subintervals, all right, with, let's say, we have the following. A is, so x naught is -2. And now the way we're going to partition is in the following way. So x1 will be, let's say, -1.6. x2 will be -0.93. x3 to be -0.21. x4 to be 0.35. What else? Let's see. X5 to be 0.82, and now X6 is 1, which is B. All right, so this is the partition. Anyway, you can pick any numbers you want. As you can see, the distance, they're not equally partitioned, so, but I don't care about that. But what I'm interested in, the first thing is to find the norm of the partition P. So find the norm of the partition P. Okay, and now that's the first task, and then we'll see what we would like to find. And now, as you can see, the norm, if we go back, you see it's here. The norm of the partition P is nothing else than the maximum of each delta xk, so we need to compute a bunch of deltas. All right, so let's do it. So let me just say the following. So I'm going to draw the following chart. So here I have subinterval. Here I have the width. Okay, and let's go with it. So the subinterval, you know the formula. In fact, let me write it again. So the width is delta xk, and the subinterval is xk minus xk minus 1. We have this. So in the first subinterval will be x1 minus x naught. Then we have x2 minus x1. Then we have x3 minus x2. Then we have x4 minus x3. Then x5 minus x4. Then x6 minus x5. Okay, so this is what we have. And now let's just write it. Let's compute this. All right, x1 minus x2. So x1 is what? So it's -1.6 minus -2. And this would give us 0.40. Okay, let's keep this in mind. x2 minus x1, so what was x2, x1, oh my goodness, I have to keep these numbers, okay, okay, so this would be what, -0.93 minus negative 1.6, right? So this would be 0.67. Now let's see, x3 minus x2 will be what? Negative 0.21 minus negative 0.93, which will be 0.72, all right? And then we have, let's see, x4 minus x3 will be 0.35 minus negative 0.21, which will be 0.56. And now x5 minus x4 will be 0.82 minus 0.35, which is nothing else than 0.47. And the last one is 1 minus 0.82, which is 0.18. And now we're going to look which one is the largest. If you look at, we can identify the largest as this guy here. So this is the largest. So we call this the largest width. So that would be the norm of the partition. So the norm of the partition is nothing else than just 0.72. All right, that's the first thing. The second thing, we would like to find the Riemann sum. So find the Riemann sum associated with the function f of x equals 2x with the given subintervals and subinterval representative. So let's just say, so we're given the following representatives. So x1 star will be negative 1.81. x2 star is negative 1.12, let's say. Let me look in the notes. Let's see what else we have here. Okay, x3 star is negative 0.55. x4 star is, let's say, negative 0.17. x5 star is 0.43. And x6 star, so we're going to take something close to 1, 0.94. All right, so these are the representatives, right? The intermediary points, this is what we call them. So now we would like to compute the Riemann sum. So we know that. That Rn, which is the Riemann sum, is nothing else than the sum from k equals 1 to 6, because we have 6 subintervals of, usually the formula is f of xk star times delta xk. All right, and here we go again. We're going to draw again a chart, and keep in mind that f of x is 2x. So we're going to let's do it like this. So f of xk star is 2xk star. All right. And now we're going to put f of xk star delta xk star. So here we have 2x1. This would be, okay, let me just, I don't want to do the computations, negative 3.62. Then 2x2 star will be negative 2.24. Okay, let me just write them. All right, so we have negative 1.10, negative 0.34, and this is 0.86 and 1.88. Okay. And now in this case, we're going to multiply them. Oh my. So we're going to have f of xk, which is be, so it will be negative 3.62 times 0.40, which would give us, okay, I'm just going to copy them from the lecture notes. Okay, so the second one is negative 2.24 times 0.67, which will be negative 1.5008. And the last one, 1.88 times 0.18. Oh my, this would be finally, what is this? 0.3384. All right. And now we're going to compute the Riemann sum. So the Riemann sum will be nothing else than just the sum of this. And well, thank God I haven't written in my notes because I didn't want to use the calculator. So the result is, by summing all these numbers here, it will be negative 3.1886. All right, so this is the result. So you see, we compute this, we just add all these numbers here. So this one, this one, this one, this one, this one, and this one, and you will get this result, right? Because the formula is given by this, keep that in mind. All right, so now we finally we can define the definite integral. So that's what we're going to do right now. So after we have the Riemann sum, as you can see, we can compute the Riemann sum. Now we define the definite integral. All right, so the definite integral, remember we said that Sn, so recall that that Sn, we dealt with the special case of a Riemann sum, keep that in mind, right? That Sn was this guy, the sum from k equals 1 to n of f of a plus k times delta k times delta x. Oh, sorry, delta x here inside. Ooch. Right? Recall that. And this is, so this is a special case of Riemann sum where the following situation happens. The subintervals right are equally spaced with delta xk is nothing else than just delta x, and this is b minus a over n. This will be nothing else than just the partition of p. And the second condition is that the subinterval representative of each subinterval right, is the right endpoint. This is important. Right? So what do I mean by that? I mean that x sub k star, right? Those points is nothing else than just a plus k times delta x. So you see, this is a special case of a Riemann sum. Okay. And now, using these information, now we can define finally the definite integral. So now the definite integral will be defined in the following way. So if f is defined on the closed interval AB, we say that f is integrable we say that f is integrable on the interval AB, right? If we have the following, if this, let's denote this by I, which is the limit as the norm of the partition is approaches 0 of the sum from k equals 1 to n of f of x k star times delta xk, right, exists. Well, we will say that this limit is called the definite integral of f from the point A, from A to the point B. That's what you need to know. And it is denoted by this guy here. So I will be nothing else than just the integral from A to B of f of x dx. Right? In other words, if you look at those two, that limit over there, provided that the limit exists, is nothing else than just the integral from A to B. And let me say a few words. Let me point out the following remark here. So remark, let me talk about the symbol, because you, in the previous lecture, we talked about indefinite integrals, right? When we didn't have any bounds. So we said the indefinite integral of f, which was the antiderivative plus constants, right? The set of constants. Well, in this case, here you see the constant is gone, and then we have only the integral from A to B, which we will call a definite integral. And there will be the so-called, well, in a future lecture, and the next lecture, you will see that we will compute this type of integrals by using the fundamental theorem of calculus. which basically is nothing else than just the antiderivative evaluated at the endpoint B minus the antiderivative evaluated at A. So it will be a number. Keep that in mind. So the definite integral of a function will always be a number. So let's point out, so we have that this integral here, this symbol, the integral from A to B of f of x dx. So we read it in this way. So this will be, this dx will be the variable of integration. Right? This b here, this guy here, b, is nothing else than the upper limit of the integration. And this will be nothing else than the lower limit of the integration. Right? And this is nothing else than just the integrand, the function. So that's what you need to know about this. Anyway, it's much more subtle than this. But anyway, that's what you need to know. And now, let me see some properties. So let's say talk about some properties. And the first one that I have in mind is the following. So the definite integral at a point. Right? And this is clear, the integral from A to A, so is nothing else, as you can imagine, is 0. So if we integrate from A to A, so there's no area under the graph, we just stick to one point, it's 0. The second property is like interchanging the limits. The limits of the integral. And in this case, we have the following. So we have that the integral from A to B of f of x dx. If we want to change those two bounds, the limits from, instead of A to B, we can write B to A. So this would be nothing else than just the integral from A to B, from B to A, sorry, but we put the negative sign of f of x dx. Okay? And now there is an important theorem. So this are the two basic important theorems that you need to know. And well, I'll talk more about more properties of integrals. In fact, let me just look and anyway, maybe we also have something like the third one is the linearity rule. Of the integral, which basically says the following. If I have, let's say, two functions, so if f and g defined on an interval a, b, when they're real valued, are integrable, then the function, let's say alpha f plus beta g, is also integrable. So where, let's say, alpha and beta are constants. And moreover, we have the following. So we will have that the integral from a to b of alpha f of x plus beta g of x dx will be nothing else than just alpha times the integral from a to b of f of x dx plus beta times the integral from a to b of g of x dx. So this is the linearity rule of the integral. Now let's see what else we have here. Well, we have also the dominant rule anyway. Of the integral. Which basically says the following. As you can imagine, if we have two functions, so again, if f and g are two integrable functions, so these are integrable. So they're integrable on the interval a, b, and f of x is less or equal than g of x for all x in a, b. Then the integral from a to b of f of x dx is less or equal than the integral from a to b of g of x dx. Right? Well, it's quite clear from the area. If you want to draw a picture, in fact, let me just draw a picture so that things will be even clearer. Let me just draw it here. A small picture. So let's just say we have, let's say we have the area of G is like this. So this is y equals G of x, the graph of this, and under we have something like this, right? So this is y equals f of x. And let's just say we have both defined on the interval AB. Well, it's quite clear that the area of under the graph, under the curve of G is greater than the area under the curve of F, right? So this is, so let's just say that this is the area of F, right? But here we have the area of G. As you can see, it's larger. We have this extra part here, so it's quite clear. And now another rule is a subdivision rule. Of the integral. Okay, and in this case, we basically says the following: for any real number C with between A and B, we have that we can write the integral I, so this is the integral from A to B of f of x dx is nothing else than just the integral from A to C of f of x dx plus the integral from C to B of f of x dx. So we're just gonna break this integral into two parts. Anyway, and I'll leave this to you, the geometric interpretation of this. All right. Now these are the main properties, and okay, there is one thing that maybe I should mention. This is a theorem. So theorem. And this is important because it tells you what happens if we have a continuous function. And in fact, in other words, when we deal with a continuous function where nothing bad is happening, because continuity will imply integrability. So the theorem says the following: if f is continuous on the interval AB, then f is integrable on AB. So continuity implies integrability, but not the other way around. Anyway, now let's just, in the remaining time, let's just deal with some examples. So the first example that I have in mind, yeah, we will evaluate this. But before, let me say one thing very important. So, and the area, yeah, because it's important before we deal with examples. So the area is the integral. So the area is an integral. So if so let f of x be continuous, and let's say f of x is greater or equal than 0, so it's non-negative on the closed interval AB. Then the area under the curve right? Y equals f of x, right? On AB, guess what? It will be nothing else, is given by the definite, so is given by the definite integral of f on the interval AB. In other words, we have the following beautiful formula. So the area of the curve, so the area under the curve, let's say under the curve, is nothing else than just the integral from a to b of f of x dx. So that's what you have to keep in mind. So this is the most important thing that you learn about definite integrals. So you have to know that this is nothing else than just the area under the curve of the curve y equals f of x, right? Okay, and now in the remaining time, I'd like to evaluate an integral, and I'm going to evaluate this the hard way, but I'm just gonna do this once because I like to use the Riemann sums, and I want you to see how we use the definition of definite integrals to evaluate an integral. But you don't have to do this. But I'm just gonna provide this example so that you can see how we do this the hard way. All right. So we want to evaluate the following integral. So the integral from -2 to 1 of 4x dx. So keep this in mind. So we want to evaluate this. And now what we're going to do is the following. So we're going to do the following. So let us choose the equally spaced n number of subintervals. So in other words, we're going to choose n subintervals equally spaced. And when we say this will be the delta x will be nothing else than just b minus a over n, usually given by the formula. But in our case, since it's on the interval -2, 1, so this would be 1 minus -2 over n, which will be 3 over n. And as you can see, as n approaches infinity, this will approach 3 over n will approach 0. All right, that's good. Also, the right endpoint of each interval right as the subinterval representative is given by xk star. It will be a plus k times delta x, which will be -2. So a is -2 plus 3k over n. And now, by using the definition, so we have that that the integral is denoted by I. So this is the integral from -2 to 1 of 4 times x dx. Is nothing else than, using the definition, is the limit as the norm of p approaches 0 of the sum from k equals 1 to n of f of x k star times delta x k, which is delta x anyway. So this would be equal to the limit as the norm of p approaches 0, right? Of, and now let's see. So this would be the sum from k equals 1 to n. And now we're going to write all this mess here. Oh my. So in here in parentheses, we have the following. So this would be 4 times a -2 plus 3k over n, right? Times delta x was what was it? 3 over n. Okay, so this would be, if we want to do continue with the computation, so this would be the limit as the norm of p approaches 0 of, oh my, let me write it again. Let me just copy this. And now you're gonna do the computations here. So this would be the limit as the norm of p approaches 0 of the sum from k equals 1 to n, right? Oh, so this would be 12 over n times, yes, 12 over n times the -2 plus 3k over n. And this will be further. So let's just take out that norm of p approaches 0. This would be equivalent with saying that this is the limit as n approaches infinity of, if you want, if we can okay, let me write like this, 12 over n, right? We're going to take this as a factor times the sum from k equals 1 to n of -2 plus 3k over n. And by expanding, applying the linearity, whatever, this would be nothing else than just, if you want to write it this way. So this would be the limit as n approaches infinity of 12 over n times the sum of -2 plus 12 over n times the sum of 3k over n. Okay. All right. And this would be equal to the limit as n approaches infinity of what? So let's break this into 2. So this will be 12 over n times the sum from k equals 1 to n of -2 plus the limit as n approaches infinity of 12 over n times the sum from k equals 1 to n of 3k over n. Anyway, so as we go further here, this would be nothing else than just so this guy here will give us what? This is, as n approaches infinity, this will give us the limit as n approaches infinity of -24. Well, this is a constant. Plus, and this guy here if you look at this, this will give us nothing else than just the limit as n approaches infinity of what? So once we know the sum of k, which is n times n plus n over 2, so I'm just going to skip this. Let me just look a bit at the notes so that, so it will be 18 times 1 plus 1 over n, according to my notes, and I think it's correct. So this would give us, in the end, will give us negative 24 plus 18, which is negative 6. All right. So that is the integral. So we evaluated the integral. All right. So, but, well, is there a way to do it in a differently than this? Well, you can do it. For example, you can choose x sub k, x k star as the midpoint of each subinterval. So you take the, so let me point out this remark, and I'll leave it to you as an exercise to continue with this. And you'll find it in my notes anyway. So one can evaluate the integral I by choosing xk star to be the midpoint of each intervals. Okay, to be the midpoint of each subinterval. Right? So you take the left endpoint plus the right endpoint and you divide it by 2. So in other words, you can write xk star as a plus k minus 1 delta x plus a plus k delta x, everything over 2. And you keep going, and then you just you know who that a is, etc. You know that a is negative 2, and you keep going. You know who delta x is, and so on. All right, guys. I think I'm going to stop here with this was the second lecture. In the third lecture, I will talk about something very, very important, and that will follow very shortly. I'll be talking about the fundamental theorem of calculus. This is one of the most, in fact, the most important formula that you will learn in this class. It is due to these two titans, I would say, both in mathematics and physics. Probably heard of them, but one of them is extremely famous. I've probably heard of Isaac Newton and Geoffrey Leibniz. So these two guys are responsible for the fundamental theorem of calculus. All right, I think now it's a good place for me to stop. Thank you very much.